Okay, so in this video, we talk about weights, co-weights, and roots of a Lie group. Okay, so where do we start? So suppose that you have a Lie group, okay? The generators of this Lie group, along with their commutation relations, form a Lie algebra. So Lie group, if you have some generators plus commutation relations, that equals the Lie algebra. Okay, now the maximal commuting subset of this Lie algebra is called a Cartan Sub-Algebra after Eli Cartan. So maximal commuting subset is equal to Cartan Sub-Algebra. Call it CSA here. Okay, now suppose that this CSA has 20 generators. Just to make it concrete. Okay, given some vector space V, each of the 20 generators can be associated with 20 matrices. So given some vector space V, then you can have a representation where the 20 generators are 20 matrices. If a vector A of the vector space V is an eigenvector of any element of the subalgebra, then the 20 matrices acting on A would produce would produce 20 eigenvalues. So A is in V. A is eigenvector of all CSA elements. Okay. What does that mean? That definitely means, so M I acting on A is going to give some number multiplied by Mi. Now, obviously, this is these are 20 different numbers, and I ranges from I ranges from 1 to 20. Okay. These 20 numbers, okay, these 20 numbers form a weight. I'll call it L. Okay. So L is equal to a collection of 20 numbers. I'll call it, let's say, eigenvalue 1, eigenvalue 2, dot, 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 eigenvalue 19, eigenvalue 20. Okay. So if you index this weight, if you put in Mi, what would you get? The output would be the eigenvalue. You input the matrix, you get the eigenvalue. Okay. A here is called a weight vector. Okay, so L is called the weight of this Lie grouper, Lie algebra. Okay, this is the weight. Okay, now in theory, if you were given some random vector space D, you won't know how many weights, how many L's exist in advance in this D representation of the Cartan subalgebra. D representation, you don't know how many weights in advance. You don't know how many you're going to encounter. Now, in practice, you work with vector spaces that you know something about. So it is possible to predict how many weights you will encounter in this vector spaces representation of the Cartan subalgebra. So usually work with vector space we know something about. Okay. Now, so in vector space V, there could be, 5 weights. I can call them, L1, L2, L3, L4, L5. In vector space W, there could be, 8 weights. I can call them, N1, N2, all the way up to like N8. And then another one, they could be 13, 20, 85, whatever. Okay. Now, let's call the original Lie algebra, the original Lie algebra, let's call it T, and let's call the Cartan subalgebra S, right? So S is a subset of T. Okay. Now T is a vector space. Okay, a Lie algebra is also a vector space, and we can talk more about that at another point. If you represent S using the T space, this is called the adjoint representation, okay, of this Lie algebra, T, of T. Okay. The adjoint action, so instead of usually a lot of representations, they use matrix multiplication, but this one, instead of matrix multiplication, the adjoint action is, is the commutator. So replace, actually, let me just say, use adjoint action. The adjoint action is just a commutator. Okay, H is an element of the Cartan subalgebra and the Cartan subalgebra S, and X is a vector in the Lie algebra or T vector space. Is in the T space. Is in the Lie algebra T, which is also a vector space. Okay. Now, here are the definitions of root and co-weight. Okay. For all elements in the Cartan subalgebra S, okay, a non-zero for, okay, a non-zero vector X in the Lie algebra Lie vector space T, okay, if it is the case that the commutator is equal to a number, which depends on h, okay, which depends on h, times x, then x we call x a you already guessed it, an eigenvector of all CSA elements. All CSA elements H. Okay. Now you can organize these in the same way that we organized weights. You can say that let's see. You can call this root L. So L eats H and out pops a number that depends on H. So L is called a root. Okay. So L eats a Cartan Sub-Algebra element H and then outputs a number. Okay. If an element of the Cartan Sub-Algebra, okay, if an element, what letter should I use? Let's use K. If K in the CSA, in the Cartan Sub-Algebra, satisfies L, let's say sub J, satisfies this, or of course you can just write this, to be honest, is an integer for all roots Lj, then we say that then K, oh my god, I gotta use, hold on. Sorry, K. Then K is a Coweight. And yeah, that's it. That is basically it. Coweights, roots, and let me zoom out a bit. And weight. That is it.